I feel really privileged to come and give a talk here. A lot of effort has gone by many people who has organized this, primarily to see that people, school teachers, school students, college teachers, all see a benefit of panorama of various subjects. So one such thing that I am going to do is discuss dimensional analysis in biology, chemistry, physics and medicine and things like that. But before I start, I am nostalgic about this place. I have been here for a very long time. The first interaction I had was I was in the main guest house here for some meeting or attending some lectures. So for breakfast, I was young then. At breakfast, I asked for some coffee or fruit juice, I forget. And then I was impatient. So I asked the person who was serving me, please give it to me in a maybe impatient voice. So he turned around and said, sir, I have served people like Professor C.V. Raman here. So that put me in place. I realized how big a place this is, how historically it's a big place. Secondly, I know several people here. One is starting from H.R. Krishnamurthy, with whom I have worked, I have done some work. And then after that, Arnab Rai Chaudhary, then Sri Ram, Deeptiman Sen. I can go on naming people here. They are all my friends. Here Usha Devi I had the privilege of knowing now, and I have learned so much of quantum physics from her. So now let me start with the beginning. Here, this dimensional analysis can be applied to almost any place. The way we start understanding dimensional analysis is the following, that we have mass, which we all know, length and time. And these are the only ones. Can everything be derived from here? The answer is no, it need not be derived from here. Energy can be derived, momentum can be derived, and velocity can be derived, and so on. That's one. Maybe there are other areas which we should look at. One of the areas which has been looked at for the last 175 years or so is information. If somebody told you information is form of energy, you would say this guy should be put in the madhouse. But that is no longer true. It started with Maxwell, with Maxwell's demon. Remember that when Carnot talked about Carnot's engine, at that time he did not know heat is a form of energy. Heat being a form of energy now, we are told in schools, so we will accept it. If somebody asks us to prove why is heat is form of energy, it will take a lot of effort. So that's the first thing, and it did take a lot of effort to find out why is information form of energy. Now, after saying heat is a form of energy, you will say, how much of heat will I equate to calories or joules? There is a famous experiment in which you keep water and go on stirring it, its temperature will increase. So you know, using the specific heat, you know how much energy. So this is the famous 4.2 times some number of joules per Kelvin. That's the answer. Can we do that for information? The answer is yes. People have done that. So this is one. I will give you an example which to my knowledge has not been completely answered. I am not an expert, so I won't know. Say take emotion. Today you would think emotion is not a part of any scientific thinking. We don't know. I mean, if you look at the history, things change. So I like to keep it as broad as possible. And today, for example, when you were giving a talk, you were mentioning about bacteria. I know that in diabetes, you have sugar level numbers. So are there numbers for bacteria? And questions like that can be asked everywhere. Like in chemistry also, you can ask the same kind of question. Maybe they are being asked. So I don't know. So what I have done is taken some simple examples and worked my way through. So that is the object of this talk. So I have written here various possibilities: biology, chemistry, physics, medicine. Again, I have written medicine. One was a heart, the other one is some drugs intake, and of course mathematics. All these are there. Let me proceed further. The first thing I will do is in mathematics, is a well-known result, is the Pythagoras theorem. Let's look at this triangle ABC. Okay, here is A, here is B, here is C. This is the triangle. Now, area of a triangle is length squared. So, I have just decided to choose C, A area is C squared is length and some angle, this angle is phi. Now, look at this triangle. I have two other triangles, ACD and CDB. The angle DCB is also phi. Why? Because that is phi and that is 90 minus phi, and triangle ACB is a right angle triangle. So, angle CDB is phi. Is that okay? Now, I use the same logic there. The area of A1, A2 has been displaced, I do not know why, d squared g phi, and A2 is c squared d phi. A2 is c squared d phi, AB is d squared d phi. So, now when I add the two, I get A squared equal to d squared plus c squared, which is of course the Pythagoras theorem. So, I have not used any other geometry, just scaling to get to the Pythagoras theorem. Is it all right? This is height versus blood pressure in animals. Again, taller animals need higher blood pressure to pump blood to the head. This is all very trivial, but still it is important to realize how dimensional analysis is used. The heart must pump blood to head against gravity. Some quantities that may be important for the problem are the height of its head above the heart, h, the volume of the blood pumped per beat per unit of beat, stroke volume, Vs, the density of blood, rho, the acceleration due to gravity g, and as well as the measure of animal's blood pressure. These quantities come from your experience. If you are not experienced, you may miss some quantities or add some irrelevant quantities. So, that is part of doing dimensional analysis. So, now I do the h is dimensions of L, rho is m by L cubed, g is L by t squared, volume is L cubed. So, you can use dimensional analysis to find out the pressure is mass, force per unit length area, so that you can just calculate and you will find this. Now, there are 5 variables you can see 1, 2, 3, 4 and 5 variables, and there are 3 dimensions m, L and t. So, you will get 2 dimensionless constants. Okay. So, these are the 2 dimensionless constants here. Now you use the knowledge of medical physics to get pi 1 is equal to s pi 2, and then you get the result, which is nothing very great, as pi 1 is proportional to p by L, p is proportional to h, which we teach in middle school. That's pressure is same thing as height. I just took this example as a matter of dimensional analysis. I will go to more difficult examples. So, P1 by Ph is equal to this, and then I go next. P1, P2 being the pressures and H1, H2. Since the animals like giraffe have long necks, about 7 times that of a human being, the blood pressure of a giraffe is about 7 times more. This calculation is simplistic and is done only to show the power of dimensional analysis. A more realistic calculation needs to consider the viscosity of the blood, radius of the blood vessels carry, and so on. This has been done, people do this and they get more complicated results, and they all agree with experiments. So, without knowing too much theory, they can get some results. Okay, that is how the whole thing goes. Okay, I got all this slides from Professor Saurendu Gupta of Tata Institute. So, though I did not formally acknowledge here, I am just saying that here. Okay, dimensional analysis and architecture. Now consider how high can we make pillars given a cross-sectional area A. If the pillar is too short, too tall, it can fall. If it is too short, then the pillar can be made thinner and the cost can be reduced. So, what is the important quantity, physical quantity to be considered? certainly the mass load, the pillar has to support MP, the area of the pillar AP, and the density of the pillar rho P. One needs a relationship of the form HP is the height of the pillar, some dimensional, some relation between MP, AP and rho P. Okay, these are the things which you are imagining will be there. Of course, there could be more complicated ones like earthquakes, what will happen and so on. We will not get into those discussions. Mass of the pillar is M, HP is L and AP is L squared. Now, we have 4 quantities. So, out of the 4 quantities, there are 2 dimensions. So, we could have 2 possible dimensionless quantities. They are pi 1 h by root AP and pi 2 pi a to the power of 3 by 2. Now, there is this IISc temple near Kumbakonam. I have seen this temple and it is pi 1 is equal to 15. Ashoka's lion column from Sarnath built 300 BC as pi 1 is equal to 15. The most impressive solid rock pillar in the world. So, we could build things like that at that time. Okay, now let me go to the next one. This is something which I teach in almost all classrooms, and those of you who are teaching physics, chemistry, please look at this carefully to see what is it all about. We start by, these are for dimensional analysis in atomic, molecular and biological system. We start by noticing the dimensions of velocity of light, the electric charge and the Planck's constant. The velocity of light, of course, is velocity, it is L by T. The dimension of the electric charge can be got by noticing the relation Es is equal to E squared by 4 pi epsilon 0 R squared. E is the electric field. This is the standard expression here which we write down, and I am working in SK, what is the set of units which we use? SK some. No, the standard units you use, I'll just say standard units, that skips me, and then energy is nothing but E squared by 4 pi epsilon naught R. E is the electric field due to 2 equal charge E, US is the energy stored in the 2 charges, separated by distance R. Finally, epsilon 0 is the permittivity of the free space. Thus, the dimensions is E0 by 4 pi epsilon naught. So, I can immediately calculate the dimension of E squared by 4 pi epsilon naught, that is m L cube by T squared. And E we all know is given by h nu, which is the Einstein's relation to understand photoelectric effect. Incidentally, there is a very interesting story about Einstein and Millikan. When Einstein had made this suggestion of E equal to h nu, photons or particles, at that time, please go back to this time when electromagnetic wave, a continuous thing, was explaining everything. There was nothing that was missing. So, when Millikan said, he said this must be wrong. So, he did the experiment on photoelectric effect and checked this, and then he writes saying, I tried my best to prove Einstein wrong, but I was wrong. And then, of course, Millikan got a Nobel Prize for this. And so, that is this. Now, E is the energy of the photon and nu is the frequency of the beam. So, h is energy. If I had put a T squared here, it would have been energy, but I have to multiply by time, so I got rid of that. Using this relation, it is easy to show that hyperfine structure constant alpha is dimensionless. Here is the famous suggested by Sommerfeld, E squared by 4 pi epsilon naught Hc is 1 by 137. Now, consider the radius of a hydrogen atom. Bohr's orbit, we teach them in schools, and class 11 or 12 we teach it, and it is given by h cross squared by me squared, and I have to put a 4 pi epsilon naught here to get the units, and n squared, n is the principal quantum number. So, n equal to 1 is the lowest orbit. How can I get this? I can get this by looking at this. Firstly, look at this quantity h by mc. If I calculate the dimension of this, the dimension of this is length. I will not do the calculation, you can do it. It's called the Compton wavelength. And here, but hydrogen atom, Bohr's hydrogen atom is non-relativistic. If it is non-relativistic, velocity of light should not enter at all. So I have to get rid of C from this equation. So how do I get rid of C? I have alpha here, which has a C. So I am divided by alpha, C will be in the numerator, so it will be cancelled. Right? It will be cancelled. So the correct answer is AB is equal to this expression which I get. And then you can do the dimensions of it. Now let us talk about the velocity of the electron in the ground state. With the velocity, one velocity is C, but C should not be there. So I divide C by R, I multiply C by C alpha. Here it is C alpha. So immediately we get an idea that the velocity of electron inside is 1/100 of the velocity of light. So it's a picture that you should keep in your mind. Then now I can calculate magnetic moment, various other quantities simply by using dimensional analysis. Is this clear? This is something which I use in a classroom, because when you teach physics or chemistry, getting the order of magnitude is very important. Whether you are talking about a needle or you are talking about an elephant, you will know what approximations to make. That's crucial. So this is another thing which I do. Now this is a very famous example of the fluid mechanist Taylor. There is an atom bomb which was exploded in somewhere in New Mexico, and it was a secret result done by the Americans before they hit the Japanese with 2 bombs, and they did not reveal how much was the energy released. Then they didn't tell British also. So the British defense people contacted Taylor and wanted to, before I have written down something there, I have skipped that, but anyway, that doesn't matter. Now, this is the general picture. I have here an atomic explosion taking place, a red spot, and then the moving air. There is a shock wave front which is moving, and atmosphere is outside. The energy released in the atomic explosion, the Taylor assumed it should be proportional to R, the radius of the explosion, density, and the time. The R is the radius of the shock wave, T is the time, and rho is the density of the surrounding air. So now you calculate this. E explosion is equal to K R to the power of X, rho to the power of Y, T to the 2. It's quite straightforward to do the algebra. I will skip the algebra here, and the answer is given here, is K R to the 5 rho T to the minus 2. Taylor knew beforehand, by looking at some other experimental data, K must be of the order of 1. In 1947, a view of the explosion was released to the public. So Taylor got hold of that article and noticed the following. He said that when T is of the order of 1 second, R is of the order of 100. So if T is of the order of 1 second, R is of the order 100, rho, the density of the air he knew, he could immediately calculate the expansion, the explosion. When he declared it, of course the American government said that this is not right. They didn't want to tell the truth, but it was right to within about a factor of 10 or so. But that itself shows how powerful dimensional argument plus your knowledge of the physics or whatever be the situation involved. It's not for the layman. It's Taylor who knew a lot of experimental details where he could figure this out. Okay. The deflection of a beam under a load. The deflection delta of a beam depends on an applied load, beam geometry, material properties and boundary conditions. For simplicity, we assume the supported beam with a point load and uniformly distributed load, as these are the common cases when deflection formula from Euler-Bernoulli beam theory, which we do this experiment in undergraduates in physics, is given by this. The goal is to find a relation between these. maximum deflection is given by that, applied load is F, Young's modulus E, moment of inertia I. You can write the dimensions of all that. I will skip again the dimensional analysis and you get this. This one was given to me by a lady, a civil engineer, Lisha Varaske, and I think that is all that I have to say. I thank Rajaram Nityananda for suggesting the talk about dimensional analysis. I have always valued his judgment and several academics. I also thank Ritesh Bharat. I thank this for suggesting this, and of course I thanked Saurav Gupta. By the way, I talked to Satyamurthy, who is a chemist, most of you know him. He has also given me many chemical reactions based on dimensional analysis. So I will stop here.
So thank you very much. I just wanted a comment on the dimension analysis in the case of velocity of an electron inside.
Okay.
So it is non-relativist. But I got reminded of the other one, but what we do as Vyskov estimates, where one looks at proton also.
Yes.
Protons.
Yes.
Protons also have less than the velocity, again using dimensional analysis.
Correct.
So that is also one thing that I got reminded. But that gives you a question on why do we do relativistic quantum mechanics then?
Why?
Relativistic quantum mechanics and hydrogen atom. So this may mislead.
No, if you do it relativistically, the formula is very complicated. So I don't know whether it can be obtained by dimensional analysis. I have not seen one. Magnetic moment can be calculated.
So let's thank Professor Mani.
Thank you very much.